going to draw a couple pictures here, out of order today, and I want you to tell me what they mean, okay? We got a velocity time graph, straight, flat, horizontal line. What does it mean? Easiest one in the world, what does it mean? Yep. I'm sorry? Yeah, it's constant velocity. Okay, you don't know what that velocity is, but it's not changing. Okay, how about this one? We got a d versus t graph that's also a straight line, but sloping upwards this time as opposed to horizontal like the last one was. Who's got this one? Yep. Good, it's also a constant velocity. I thought I might trick you on that one. If we're doing v versus t graphs, this one would represent a constant acceleration. But for a position time graph, it represents a constant velocity. What about this one? That should be a straight line. It's not perfect, but okay, straight line sloping downwards. What does this one represent? Yep. No, it's not a constant deceleration. Yeah, it's a constant velocity, but can you be more specific on that one? Constant velocity that is, yeah, in the negative direction, right? So it's like driving to Calgary. This one would be driving to Calgary. This one would be driving back from Calgary. Not necessarily in reverse, just going in the negative direction. Okay, if we have a v versus t graph that has that same shape, then what does that one represent? Velocity is changing, right? You can see at every given moment in time, the velocity is different. Okay, specifically, the velocity is decreasing. It's an acceleration. It's a deceleration, right? Or we could say a constant negative acceleration. Let's go one or two more here. Let's go v versus t graph that looks like this. What do you got there? Thank you, John, for putting up your hand so quickly. Good, increasing acceleration. Not only is the velocity increasing, so it's accelerating, but the rate at which the velocity increases. In other words, the acceleration itself is increasing. What about this one? Position time graph looks like this. Thanks for putting up your hand, Luis. Yeah, that's a tough one, actually. It could be. Yeah, Luis said, if you didn't hear, guys, the rate of acceleration is decreasing. The acceleration itself is decreasing. It could be. We don't really know that for sure in this question. We know that it's slowing down. Okay, we know that it's decelerating. Okay, because the position is getting bigger. Yeah, it's a position time graph. Okay. The velocity is decreasing, therefore it's decelerating, and we don't know if it's decelerating at a constant rate or not. The deceleration may be changing, but we don't know that for sure based on the shape. We just know that it's decelerating. If Luis got it mixed up there, I think, with a v versus t graph, right? If it looked like this on a v versus t graph, then we know that the rate of acceleration, still accelerating, but the rate of acceleration is decreasing. Right? Be careful, guys. I haven't made up tomorrow's quiz yet. Maybe I throw some of these shapes on there. Maybe I don't throw some of these shapes on there. Maybe I put in a d versus t graph in there to see if you're paying attention. Maybe I don't put a d versus t graph in there to see if you're paying attention. Just be aware of that, okay? Okay, pay really close attention to that. Might not be a bad idea when you see one of these graphs just to circle the y-axis, just to draw attention to the fact that it's either d or velocity, position or velocity, so that you don't get that mixed up. All right, let's draw a picture of a velocity time graph. We'll make time in seconds and velocity in meters per second. Let's make it look something like this. Let's go 5 seconds, let's go 10 seconds, let's go 15 seconds, and let's make this 10 meters per second. I want to find right now the velocity at 8 seconds. How do we get the velocity at 8 seconds? I'll give you a hint. It's easy. Yep. Yeah, we're going to go up and over, right? If you want to find position on a position time graph, it's up and over. Velocity on a velocity time graph, it's up and over. So 8 seconds, up and over, the velocity would be 10 meters per second. Hey, what's the change in velocity between 0 and 5 seconds? What's the change in velocity between 0 and 5 seconds? Anyone? This one's an easy one as well. 10 meters per second. Good. We're going to say final minus initial. The final at 5 seconds is 10. The initial at 0 seconds is 0. 10 minus 0 is 0. What's the change in velocity between 10 and 15 seconds? That's a little bit of a tougher one. It's still not that bad, but it's a little bit tougher than the one that Joe just did for us. Between 10 and 15 seconds, the change in velocity. Final minus initial, right? What's the final at the end of 15 seconds? 5 meters per second. What's the initial? 10. What's 5 minus 10? Negative 5.0 meters per second. What about the acceleration now? Let's go to the acceleration between 10 and 15 seconds. The acceleration is the, how do we find that? Don't tell me what the answer is. Just tell me how you'd find it. One word. Starts with an S. It's the slope. The slope is going to be y2 minus y1. It's going to be 5 minus 10 over x2 minus x1, 15 minus 10. That gives me negative 5 over 5. The slope is going to be equal to negative 1.0 meters per second squared. So the acceleration would be negative 1.0 meters per second squared. It's slowing down at 1.0 meters per second squared. Finally, one more. Let's get the displacement. This is the hardest one that we've done on any graph. How do we find the displacement on a velocity time graph? Some of you guys were having trouble with this a little bit yesterday. One word. Starts with N. Starts with a vowel. Starts with N. A. Yes. What is it? The area. Right. Let's break it up like this. Okay, we've got a triangle here. We'll call that A1, A2, A3, and A4. A1 is a triangle, so it's going to be 1/2 a base times height, 1/2 of 5 times 10. It's going to give me 25 meters. A2 is a rectangle. This one's easy. Base times height. The base is 5 to 10, so it's 5. The height is 10. The area is 50 meters. The third one is a triangle again, so it's 1/2 base times height. The base is 5. Goes from 10 to 15. The height goes from 5 to 10, so it's also 5. That gives me 12.5. And finally, A4 is a rectangle, base times height. 5 times 5 is 25. We add those together. We end up getting 112.5 meters. Is that okay? Okay, if I give you that question on tomorrow's quiz, how many people would have got 100? Then where were your hands? How many people would have did pretty well on it? Maybe not 100, but good on this quiz. Review this stuff tonight. Come and see me during scheduled help tomorrow if you need to. You guys have the benefit of having Physics 20 last period of the day. Okay, if you have a quiz last period of the day and you're having trouble with the stuff that the quiz is on, then you can come and see me. Okay, we get some help on that stuff, okay? Now, we did do one more new thing yesterday here. This was really, really quick. Just the shapes of acceleration time graphs. This is not going to be on your quiz tomorrow, okay? It'll be straight velocity time graphs. But I'm going to review that nonetheless. Tell me what the first one means here. You could give this to me in as little as 2 words here. What is it? Good, increasing acceleration. It's speeding up, but the rate at which it's speeding up is increasing. So it's an increasing acceleration. What about this one? Yeah. Yeah, everyone always likes to think that this one is constant velocity or it's stopped. The most common answer actually is it's stopped because they see that flat horizontal line, right? But you can see that there is an acceleration here. It's speeding up the whole time. It's just not increasing the rate at which it's speeding up. It's a constant acceleration. This one, what's this one? Yep. Good, it's decreasing acceleration. Is it going forward or backwards? Probably going forwards, okay? And it's speeding up going forwards. It's not slowing down, it's not going backwards. It's speeding up going forwards. It's just not speeding up as quickly as it was before. The rate at which it speeds up is decreasing. All right. Today, I want to kind of go back a little bit and kind of go forward a little bit all at the same time. We're going to talk today about the acceleration due to gravity. This is largely like the acceleration problems that we've done before the break. But there's one added thing to it. One added thing that actually makes most of these questions a little bit easier because it provides us with an additional given. We'll talk about what that is in just a second. I want to do a quick little demonstration for you here right now, though, okay? All right, so you just saw from the demonstration that we did with the piece of paper and the keys, that when we dropped them both, crumpled up the piece of paper, we dropped the piece of paper and we dropped the keys, they both fell at exactly the same rate and hit the ground at the same time. That told us that those objects both accelerated at the same rate. We know the rate of acceleration of any object on Earth. It is more or less negative 9.81 meters per second squared. Now, put a little asterisk by that, because that value does change actually a little bit depending upon where you are. If you're in Vancouver, it's a little bit higher than 9.81. If you're at the top of Mount Everest, it's a little bit lower than 9.81, but it's pretty close to this value no matter where you are on Earth. Every object, in the absence of air resistance, will fall at exactly the same rate. That rate will be approximately neg 9.81 meters per second squared. Now, similarly, all objects that are rising will also accelerate at negative 9.81 meters per second squared. So if I drop a ball from the top of a building, it'll fall at neg 9.81. If I throw a ball up in the air from the ground, it will rise at an acceleration of neg 9.81. Can anybody explain that for me? Can anybody explain how, first of all, the rate of both of them, the falling and the rising, is 9.81, and second of all, why it's negative for both of them? What is it that's causing gravity? Okay, if I'm standing on Earth and I throw a ball up into the air, or I stand on the top of a building and drop a ball, what is it that's causing gravity? This is an easy question. What's causing gravity here? What's causing gravity here? The Earth. Right, the Earth is causing gravity. If the Earth is causing the gravity on the ball that's falling, and the Earth is causing gravity on the object that's rising, then they both should accelerate at the same rate, right? Well, let's look at the negatives. Okay, we can see the object that's falling should experience a negative acceleration because it's a downward acceleration, right? But what about the object that's rising? Why is it a negative acceleration? Yep. Yes, okay, yep. Fundamentally, the force of gravity is always downward toward the Earth, and therefore the acceleration is always downward toward the Earth. Okay, but let's look at it on not quite so fundamental of a level. If the object is falling, it's speeding up in the negative direction. If the object is rising, it's slowing down in the positive direction. Either one of those give you a negative acceleration. Speeding up in a positive direction, speeding up in a negative direction, or slowing down in a positive direction. They both give you a negative acceleration. So regardless, when an object moves through the air, it accelerates downwards. Whether it's rising up or down, falling down, it accelerates downward at a rate of neg 9.81 meters per second squared. Okay, in general, acceleration is negative when an object slows down in the positive direction. That's when the object is going up, right? Or when it speeds up in the negative direction. That's when the object is falling down. All right, so what are we going to do with this? This whole idea of gravity and the acceleration of gravity, negative 9.81 meters per second squared. Well, we're going to solve problems that are real similar to problems that we've solved before, but now the object will always be either rising up into the air or falling. This is good because it gives us a given automatically. In every question that we're going to do today, the acceleration will be negative 9.81 meters per second squared. So even if it doesn't tell us what the rate of acceleration is, we know what it is. Okay, that doesn't change the questions we've already done 2 weeks ago before the break. Okay, if a car was speeding up from a stop sign, okay, and accelerating to 30 meters per second, the acceleration is not 9.81 meters per second squared. But for falling objects and rising objects, it is, and it always will be. We're going to use the same equations that we've learned before, the group B equations, because these problems all involve acceleration. Let's take a look at an example here. 1.17 on page 57. It says, while cliff diving in Mexico, a diver throws a smooth, round rock. They're telling you it's a smooth, round rock. Why? Okay, that isn't really going to change the way we're going to do this question, but they're kind of just telling us that we can assume something by telling us it's a smooth, round rock. John? Yeah, it's fairly aerodynamic, and there's not going to be a lot of air resistance. So we'll ignore air resistance here. Good. It throws it straight down with an initial speed of 4.0 meters per second. If the rock takes 2.5 seconds to land in the water, how high is the cliff? A couple summers ago, my family and I went to a place called Maple Lake in BC. Does anybody know where that is? Near Vernon. You know where Maple Lake is? Yeah. You ever been there? I'm sorry? Okay. My brother-in-law and sister-in-law have a place near the lake in Maple Lake. So you go out there for a week in the summertime and go boating and go swimming and whatever. And I remember a couple summers ago we went boating and found this cliff near the water, well, on the water, but kind of off in a corner of the lake. It's a massive lake. We found this cliff off in the corner of the lake and decided we're going to climb this cliff and go jumping and jump off this cliff into the water. A great place to do it because the cliff is pretty much straight down like this. And then when it hits the water, you can tell this by a depth gauge in the boat. Okay, you got the boat parked right here. Okay, depth gauge in the boat tells you that the water there, even right next to this cliff, right near the shore, is about 100 meters deep. Like the length of the football field deep. So it's a good place to jump off a cliff because you're not going to hit the bottom. Okay, you got to be moving pretty fast to go through 100 meters of water. So we climb up, not straight up. There's kind of a path, kind of around to go up, and then you jump off this cliff down here. Let me tell you, you go up, you're sitting in the boat and you're thinking, oh, that's not that high. And then when you climb up to the top and you look down, and you can see down as far as, like you can't see the bottom because it's 100 meters deep. It's terrifying when you're standing up there. It's absolutely terrifying when you're standing up there ready to jump. But you can't get down any other way because the way that we climbed up, you just couldn't go down that way. It would be impossible to go down that way. So I remember the first time I went, I stood up there for probably about 10 minutes, terrified. Finally, I jumped. And it was a blast when I actually did it. So I did it again and again and again. The first time was terrifying. But I remember at one point, myself and my brother-in-law, my sister-in-law, my wife, my son, my nephew, and my niece, we're all kind of wondering, I wonder how high this is. Like, I wonder how high this cliff is. So we decided we'd do something similar to what's here. Okay, we didn't throw a rock down with an initial speed of 4.0 meters per second. We just dropped it. Almost identical to this question, except instead of having an initial velocity, VI, of 4.0 meters per second, or I should say -4 because it was thrown downwards, we had an initial velocity of 0. What do? We timed it. We timed how long it took the rock to fall and hit the water. And then we did exactly the same thing as we're going to do right now. We calculated the displacement of the rock, how far the rock fell. That told us how far we fell, the height of the cliff. Ended up being about 10 meters, which doesn't sound all that far, like 30 feet, 10 meters, doesn't sound all that high. But let me tell you, when you're standing at the top of it and looking down, it's high. At least the first time, it seems really, really high. Okay, so we got an initial velocity of -4 because it's going downwards. We have a time here of 2.5 seconds. I told you already we're looking for the displacement. Okay, that will give us the height of the cliff. Is there anything else that we have here if we read between the lines? Boy, oh boy, you better get this, Joe. Yeah. Everything that's falling or rising has an acceleration of negative 9.81 meters per second squared. Okay, it's a group B problem, right? Because it involves acceleration. Which equation do you want to use? Take a look at your data sheets. They're not written on the board here right now, so take a look at your data sheets, please. You know which ones are group A and which ones are group B. See which one seems to fit the best. Genesee, you have one there? Okay, let's try that one. D is equal to VIT plus 1/2 AT squared. It's a valid equation for sure, so worst case scenario is it doesn't work for us. We try something else. VI is -4. Make sure you make it a -4 because it's accelerating downwards. T is 2.50 seconds plus 1/2 of negative 9.81. Again, make sure that you make it a negative value because it's speeding up in the downward direction. And then T again is 2.50. Don't forget to square that. Let's pull the calculator out here and do this as a group here. We're going to say -4 times 2.5. Okay, it gives me -10. Let's add to this bracket 0.5 times negative 9.81, not positive, negative 9.81 times 2.5 squared. Let's end that bracket. We get negative 40.65 meters. Negative 40.66 it actually was, which technically should be rounded to 3 digits. So we'll make it negative 40.7 meters. Is that the height of the cliff? That's how far the rock fell. Isn't that the same thing? Almost. If the rock fell negative 40.7 meters, right? Negative because it fell downward, then what's the height of the cliff? Right, you got it? We're not making a big jump here, guys, okay? If the rock fell neg 40.7, then the height of the cliff is? What is it? Somebody said it over here, I think. Positive 40.7. Height's a scalar, right? So the height of the cliff is 40.7 if the rock fell negative 40.7. Having said that, okay, if you're doing this question and you leave the answer right there as neg 40.7, I'll mark that right. Even though technically you haven't found the height, you found the displacement of the rock. I'd still mark it right. Okay, does that make sense? This is no different than the questions we've done 2 weeks ago, right? Except that A is neg 9.81 instead of positive 3.2 or negative 4.7. Okay, A is always neg 9.81. Yep. Yeah, that's true. That's true. It's a good point. It does depend upon where you drop the rock from, whether you're standing and, I'm in Maple Lake again here. I'm standing like this. Okay, if I drop the rock from right here, then I haven't really measured the height of the cliff. I've measured the height of my hand above the water, right? Okay, but when you're talking about a 40-meter distance, the height of your hand isn't adding much to it. Maybe, maybe a half a meter to it, but not a huge amount. Okay, does that make sense, guys? Okay, let's take a look at those 3 questions then. Again, treat them like you did all those other acceleration questions, but this time A will be neg 9.81 in each of these cases. In almost all of these cases. In 2 of these cases. Question number 3 is a little bit different. So let's see what we can do with them, and then we'll take a look at them as a group here in a bit, okay? Let's take a look at number 1. It says if a rock falls 0.75 seconds to hit the ground after being thrown down from a height of 4.8 meters, determine the rock's initial velocity. So the time interval here is 0.750 seconds. The acceleration, as we know, is neg 9.81. Don't forget to put that vector sign over it, okay? That may seem like a small thing, but by putting that vector sign over top of the A, it reminds us a little bit, at least, that it's a vector and that we need to put a negative in there. Okay, it helps us to avoid forgetting the negative value. Now, the displacement of this rock, here's the one where a lot of people are making mistakes on. the displacement of this rock is not 4.80 meters, like I have written down there. What is it? It's negative, because it falls. The rock has fallen 4.8. It ends up 4.8 below where it started. So we've got to make sure that we make that a negative value. We want to determine what VI is. Ryan earlier suggested to me that maybe VF was 0 here. Can we write that down? We can't. The argument here is that it hits the ground, right? So it stops when it hits the ground. No, it stops after it hits the ground, not when it hits the ground. Ryan, can I have you come up to the front there for a second? I'm going to use you as a volunteer, okay? Okay, Ryan's going to have a seat in this chair. He's going to pull it down towards that middle desk there, Ryan, if you want to head down to the middle desk in the room there. Okay, now Ryan's going to sit down in that chair, and on the count of 3, you guys give me the count of 3, I'm going to drop this hole puncher on his head, okay? Okay, on the count of 3, ready? 1, 2, 3. I'm not going to drop the hole puncher on his head, right? Why not? It's going to hurt. It's going to hurt. Why is it going to hurt? Because it's not moving when it hits his head? Of course it's moving when it hits his head, right? Just the same as it's moving when it hits the ground. It's not moving after it hits his head. It's not moving after it hits the ground, but when it hits, it's moving, right? So is this object, is this rock moving when it hits the ground? Yes, it is. It's not moving after it hits, after it stops, right? It's done. But that's another problem. Okay, that's the deceleration of the rock in contact with the ground. The acceleration as it falls, the final velocity is not 0. We don't know what it is, so we can't write that down. Ryan, that's a pretty common misconception. Okay, there's a lot of people in this room that were thinking the same thing, just didn't say anything about it, okay? When an object falls and it hits the ground, it's not 0 for the final velocity. Remember that. Okay, we want to find VI here. The equation that we probably want to use here, D is equal to VIT plus 1/2 AT squared. That's the one that most people seem to pick, and that's the one that I would probably go with as well. Now we're looking for VI. This is a tough one to rearrange for VI. Remember the rule? Get rid of what's not attached first. Get rid of what's not attached first. What's not attached to VI here? What's not connected to it? Yeah, 1/2 AT squared. So since 1/2 AT squared is added to this, let's take it over to the other side by subtracting. It becomes D minus 1/2 AT squared equals VIT. Make sense? Now we got to get rid of the T because it is connected. So how are we going to get rid of the T here? Take that over, we're dividing, guys. We end up with D minus 1/2 AT squared. Let's divide it by T. We end up getting VI. How many people got that? Good, good. For those of you who did, very good. That's a tough one to rearrange. Okay, now we can plug our numbers in. It's still not pretty here. D is neg 4.80 meters. Subtract 1/2 of neg 9.81 times T squared, 0.750 squared. Let's divide that by the time of 0.750. Okay, let's pull out the calculator again for this one because it's kind of ugly. Let's get that second term first. Let's say 0.5 times neg 9.81 times, fix that up there, neg 9.81 times 0.75 squared. Okay, that's the second term, negative 2.75. Now let's say negative 4.8, subtract that number. Okay, negative 4.8 here. Subtract the term that I just found. We end up getting negative 2.04. Now let's divide that by 0.75. And we end up getting negative 2.72. VI is neg 2.72, which is exactly what they tell us the answer is. They actually say it's 2.72 down. What's the difference here? I said neg 2.72. They said 2.72 down. That's the same thing, right? Okay, we good with that? Yeah, Jazzy?
When we substituted
Yep.
2.750,
Yep.
why is it?
When we divided it, you mean?
Yeah.
Yep.
Isn't it negative?
Tell me why it is negative 7.750. Why would we make it a negative? Okay. No, I mean, so you asked me why we don't make it a negative. Okay. The real question is why would we make it a negative? Basically, what I'm saying is don't make it a negative unless you have a reason to make it negative. Okay. If you have a reason to make it negative, then I can answer that and say, okay, well, no, that's reason's wrong because blah, blah, blah. But if you don't have a reason to make it negative, then don't make it negative. Okay. In the end, time's a scalar, right? So time is always going to be a positive value. Now, we may subtract a time at some point, but time itself is always going to be positive. Okay? Okay, let's take a look at question number 2 as well. I think that's a challenging one as well. And then that's probably where we'll wrap it up for the day. 2 says, having scored a touchdown, a football player spikes the ball in the end zone. The ball was thrown down with an initial velocity of 2 meters per second. We're going to make that negative 2 because it's thrown downward. From a height of 1.75 meters, we're going to make that negative 1.75 because that's how far it falls downwards. And we'll make the acceleration again negative 9.81, as we always do when an object is falling or rising. We want to find t. Now, I would bet anything that what most of you tried to do is this equation, d is equal to vit plus 1/2 at squared. How many people tried this? That's right. That's a correct equation. The only problem here is that we're solving for t, and that's a pain in the butt to solve for. You need something called the quadratic equation to solve for that t. How many people have ever heard of the quadratic equation? About half of you. Okay. We will not, there's no question that you'll see this year that will force you to use the quadratic equation. There'll always be another option. You can use it, but you're not going to ever have to use it. So, if there's another way to do this question without the quadratic equation, then we better find another equation. Let's try this. Vf squared is equal to Vi squared plus 2AD. Vf is equal to the square root of 2 squared. You notice I dropped the negative in there? Anybody know why? Okay. Yeah, because this is speed, not velocity. Right? The velocity is negative, but the speed is positive. This is still negative. This is still negative. Okay, let's get that final speed, even though that's not what we're looking for. Let's get it, because at least it's something. Say 2 squared plus 2 times neg 9.81 times neg 1.75. Let's square root that. We end up getting a VF of 6.1915 meters per second. Clearly, we're not done here. That's not what we were looking for. We're looking for T. Does anybody have a thought now that we have VF, though? Does this make the question easier? How about this? Rearrange that. Vi plus Vf over 2 is multiplied by T, so let's divide by that. D over Vi plus Vf equals T. Okay, so let's sub in some numbers here. D was neg 1.75. Vi was neg 2. Vf was negative 6.1915. Remember when we found this up here, it was the speed. We want the velocity in this. Neg 6.1915 divided by 2. That equals T. So let's find this now. Let's get the bottom one first. Neg 2 subtract 6.1915. Let's divide that by 2. Let's say negative 1.75. Divided by that. Gives me 0.427. And that's the answer, 0.43 seconds. How many people got question number 2? Couple people? That's a hard question. Okay, that's a hard question. Okay, you have no extra homework tonight. Please make sure these 3 questions are finished, though, to the best of your ability. And if you have any issues with them tomorrow, question number 3 particularly, then just make sure you ask me, okay? Quiz tomorrow, remember, it's not on this stuff. The quiz tomorrow is on the B versus T graph, so make sure you're ready for that as well. If you have any questions, see me sometime during the day before we have the quiz, okay? Lunchtime, whatever. Okay, that's it for today, guys.